The electricity grid has a heartbeat. It beats 50 times per second. Every generator, every wire, every substation is synchronized to that rhythm. If it speeds up, turbines trip offline. If it slows down, the lights go out. This is the physical reality beneath every energy trade. In the last video, we compared the electricity grid to a lake with no dam. Let's push that further. Electricity is the only commodity that must balance supply and demand within milliseconds. Not minutes, milliseconds. There is no warehouse. You cannot stack electricity on a shelf and sell it next week. The UK grid operates at 50 Hz. That frequency is the rotational speed of every generator connected to the system. When supply exceeds demand, turbines spin faster, frequency rises. When demand exceeds supply, they slow down. If frequency drops below 49 Hz, automatic systems start disconnecting industrial users. Below that, you're looking at a cascading blackout. Batteries exist, but the scale is tiny. The UK uses 30 to 40 gigawatts continuously. Even large batteries run out in a few hours. So where does all of this happen? The grid has 4 layers. Generation, power plants, wind farms, solar panels. They produce the electricity. Transmission, high voltage wires that carry power over long distances. Think of this as the motorway network, a Scottish wind farm sending power to London. Distribution, lower voltage networks that deliver power to homes and businesses, the local roads. And consumption, everything that uses electricity, homes, factories, data centres. When you trade UK power, you're trading at the transmission level, the right to inject or withdraw power from the high voltage grid. Somebody has to keep this whole system balanced, second by second. That somebody is the system operator. In the UK, it's NESO, the National Energy System Operator. Think of them as air traffic controllers. They don't fly the planes, they coordinate everyone else to prevent collisions. NESO's main tool is the balancing mechanism. Throughout the day, they issue instructions to generators. Increase output by 50 megawatts, decrease by 100. If wind drops unexpectedly or a power plant trips offline, the balancing mechanism responds within minutes. Now here's the part that keeps traders awake at night. If you're out of balance, you don't just pay the market price, you pay the imbalance price. You sold 100 megawatt hours day ahead at £80. Your wind farm only generated 80. You're short 20 megawatt hours. During that settlement period, the system was stressed. The imbalance price spiked to £220. You buy back those 20 megawatt hours at the imbalance price. That's £4,400, just to cover a 20% forecast error. One bad settlement period and you've lost more than half your profit. To understand why electricity costs what it costs, you need to know how different plants generate it. Nuclear. Uranium fission produces heat, which makes steam, which spins a turbine. The fuel cost is tiny, just a few pence per megawatt hour. But nuclear plants are slow. Shutting one down and restarting it takes days, so they run constantly, regardless of price. Gas turbines work like jet engines. Burn gas, spin blades. An open-cycle gas turbine starts in under 15 minutes, but only converts about a third of the fuel's energy into electricity. A combined cycle plant captures the waste heat to drive a second turbine, pushing efficiency above 50%. More efficient, but slower to start. Wind and solar have no fuel cost at all. The wind is free, but their output depends on the weather, not on price. And crucially, they have no spinning mass. The heavy rotating turbines in nuclear and gas plants act like flywheels, keeping the frequency steady. Solar panels don't do that. So NESO has all these different plants available. Some are cheap, some are expensive. How does it decide which ones to run? The answer is the merit order. NESO stacks every available generator from cheapest to most expensive. Wind first, because the fuel is free. Then nuclear. Then gas plants, ranked by efficiency. Expensive peakers at the top. It dispatches from the bottom and works upward until demand is met. At 35 gigawatts of demand, the last plant needed is a modern gas turbine at £60 per megawatt hour. That plant, the marginal generator, sets the price. And everyone gets paid that price, including the wind farms that bid zero. Wind farms getting paid the gas price, even though their fuel is free. That's how electricity markets work. The marginal generator sets the clearing price for everyone. Now watch what happens when demand rises to 42 gigawatts. NESO needs more capacity. Older, less efficient gas plants come online. The clearing price jumps from £60 to £75, a 20% increase in demand, a 25% jump in price. That is why power prices are so volatile. In the first video, we opened with negative prices. Electricity worth less than nothing. Now you can see why. When the wind is blowing hard and demand is low, you can have 45 gigawatts of zero-cost generation. Wind, solar, nuclear. If demand is only 32 gigawatts, there's more supply than the grid needs. So why don't generators just switch off? Nuclear can't. Shutting down for a few hours costs millions. They'd rather pay the negative price. And wind farms on government-backed contracts actually earn more when prices go negative. Their contract guarantees a strike price, say £60. If the market clears at -50, the contract pays them the difference, £110 per megawatt hour. They're making more money than usual, so generators pay to stay connected. Negative prices aren't a bug, they're the system working exactly as designed. Everything we've described so far applies to electricity. Gas is a different world. The fundamental difference is storage. Pipelines hold gas under pressure. That's called line pack. Underground storage facilities can hold billions of cubic meters for months. If a gas trader misjudges demand by an hour, the system absorbs it. If a power trader misjudges by a minute, frequency drops and alarms go off. Gas traders manage their own portfolios. They submit forecasts of how much gas they'll put in and take out. If they're wrong, they pay an imbalance charge. But the system doesn't collapse. The buffer absorbs it. When you hear people say the gas market is self-balancing and the power market is centrally dispatched, this is what they mean. Gas has a cushion. Power does not. Now, there's a physical problem hiding inside this system. The UK's wind capacity is concentrated in Scotland. Offshore farms in the North Sea, onshore farms in the Highlands. But demand is concentrated in England, especially the southeast. Between Scotland and England, there's a transmission bottleneck. The wires can only carry about 5 to 7 gigawatts. When Scottish wind is generating heavily and the wires are full, the excess power has nowhere to go. So NESO pays the wind farms to turn off. That's called curtailment. At the same time, NESO pays gas plants in England to turn on to cover the shortfall. In 2025, the UK paid roughly £1 billion in curtailment costs. £1 billion to turn off wind farms that were generating perfectly good electricity because the wires couldn't carry it south. For a trader, this is basis risk. The price where your asset sits is not the price where you hedged. Before 2010, the merit order was simpler. Nuclear provided baseload, coal and gas competed in the middle. Prices were relatively stable because fuel prices moved slowly. Then, wind and solar arrived at scale. By 2026, the UK has roughly 36 gigawatts of wind and 24 gigawatts of solar. On a windy, sunny afternoon, renewables can cover nearly all demand. The merit order is no longer a stable stack. It shifts with the weather, hour by hour. The same time slot might clear at £20 one week and £100 the next, depending entirely on the wind. Forecasting isn't just useful for power traders, it's existential. Every price spike, every negative hour, every imbalance penalty traces back to what you've seen here. Pipes, wires, and the merit order, the physical constraints that define how energy markets move. This video is part of a growing library of guides Jordan has written, covering everything from forward curves and spark spreads to position management, settlement, and BESS operational readiness. One product manager at EDF said he wished he'd had them during his PhD. A senior developer at an energy trading company called them incredibly insightful, easy to read and understand. The full guide library is available to members of Jordan's school community and to students on his energy trading boot camps. Links are in the description. Subscribe! The next video covers the spark spread, how traders decide whether a gas plant should run,